What's up, Algebra 1? So we are going to be talking a little bit about the very first homework assignment in Module 2, and a lot of it is bridging from the first chapter that has to do with sequences, but specifically has a lot to do with arithmetic sequences, because all of Chapter 2, all of Module 2 is about linear functions. And linear is a concept of adding or subtracting in a common pattern, just like arithmetic is. So let's jump into a little bit of practice. It tells you that you're given a function, f of n equals 5n minus 7, and then they also say that it can be represented explicitly using that formula from the first chapter. A sub 1 plus the common difference of 5, and then the n minus 1 part. So basically it says we'll help James by figuring out how you can go from this formula to the function notation formula. And really it's some pretty quick steps. First thing we're going to start with is distribution. Distributing that 5 times n and 5 times negative 1. And then taking a moment to just simplify. Negative 2 minus 5 is negative 7. And so now we have a more simplified function that we can plug values into to calculate future values in the sequence. So part B is actually figuring out what those values are. So if you take your function over here and you replace n with 1, 5 times 1 is 5, minus 7 is negative 2. And if you keep plugging in different values of n, let's say you plugged in 2 here, well, 2 times 5 is 10, minus 7 is 3. And so if you were to look at those discrete points on a graph, remember the word discrete from chapter 1 just means only points. The opposite of discrete is continuous, but we're not going to do that for this graph because sequences are the first number, the second number, the third number, not the 1.2 number or the 3.4 number. So it's only seeing these specific points, and there's no points in between any two terms. So this next part says determine whether each table of values represents a linear function. And so these are all functions because none of the x values are repeating. But if it's a linear function, then it has what's called a constant rate of change. And when we hear the phrase rate of change, even the word average in front of it, average rate of change, that all means slope. Okay? So what we're looking for here is we're looking at the table and we say, okay, the left side's adding 1 consistently. However, the right side seems to add a little more each time. So I'm not sure that's a function that's linear. It may seem a little bit linear at first, but it's going to eventually start curving, and so that one is definitely not. So for those that represent a linear function, write what the function is. For those that aren't, explain why not. So this one is not going to be a linear function. It's a function, it's just not a linear function. So when I look at this one, I see more consistency. The left side adds 1 every time, and the right side seems to be subtracting 3. So we're going to try to build a model here, thinking about ax plus b. You may have thought it as mx plus b in a former class, but we're going to think about it as the slope value, the rate of change, which in this one is negative 3. Negative 3 represents how you are seeing the output change constantly by the same amount. And then if you're really slick, you can pull the y-intercept from the table. So this right here is your y-intercept value, 0, 2. So what that means is if I was to plug in 0, I'm supposed to get out 2. So that must be my y-intercept, or my b value. Think about it. Negative 3 times 0 is 0, plus 2 gives you exactly 2. Let's test another point. 3 times negative 3 would make negative 9, and if you add 2 to that, well, guess what? You get negative 7. So that does work. My equation needs to be tested before I move on, just to make sure that I did it correctly. So this one is also a linear function. We see the left is always adding 1. We see the right is always adding 5. And so for this one, we kind of have to imagine what would the y-intercept be if we were back at 0. So I'll let you think about that for the homework that's on your own. I want you to tell me what would the equation have to be so that when you plug in 4, you get out 26. Or if you plug in 3, you get out 21. And it should follow very similarly with what we did in the second question. calculate the average rate of change. So over here, I just picked two random points. I picked the last one, and I picked the first one. And so in the formula, you have y2 minus y1 over x2 minus x1. So that's what I wrote here at the very top. This is the slope formula. And so I basically said, let's plug in 14 minus negative 4, and we'll also do 12 minus 3. So I want you to go ahead and simplify that as far as you can, and we'll check your work tomorrow. Similar in a graph, the idea of the average rate of change is the idea of the rise over the run. And so I picked 2 points here, the x-intercept and the y-intercept. Those are really good points to kind of analyze here. And so I want you to think about, if I use the formula, what would I get? And then I want you to think about, well, how much does it fall and run? Okay, the fact that it's falling means that we have a negative slope here. And if you think about the graph, it is decreasing from left to right. So we definitely will get a negative value for that second one. Okay, so go ahead and try that, and we'll check your work tomorrow. So the stretch here gives us a word problem. It says Craig left his house at noon and drove 50 miles per hour until 3 p.m. Then he drove the next 5 hours at 70 miles per hour, and they want us to kind of figure out what's his average rate of change for the entire trip. So at noon, he has driven no hours and no miles. So at 1 o'clock, so 1 hour later, it says that he's gone 50 miles. So I'm going to put that in my table. Tables just kind of help me think about the problem as we're exploring it. So we're actually doing that until 3 p.m. So another 50 miles, you've driven 100. And then at 3 p.m., you're at 150. Well, for the next 5 hours, we're not going to be increasing by 50. We're increasing by 70. So in that fourth hour, 150 plus 70 makes 220. Add 70 to that at 5 o'clock, you're at 300. And I want you to just keep on until you get to that very last value. In 8 hours, how much have you driven? So I'm going to put a question mark there. That's your homework, to figure out what that value would be. So now if we're doing average rate of change, that's slope for the entire trip, I'm going to jump into the slope formula. And I know most of this information, okay? I don't know the question mark. I don't know how far you ultimately drove, but I am going to subtract the fact that you started at 0 miles. Same thing for the hours. I'm going to say that you ended at 8 hours, but you originally were at 0. And so if you can figure out this question mark, we can then simplify and know what is the average rate of change for the entire trip. The last little part is about function notation. So this is called f of x right here. And so when they replace that value in parentheses, that's secretly the x value they want you to plug in. So for the first one, if I'm doing f of 0, I would say, well, 3 times 0 is 0, and minus 10 gives me negative 10. Or 3 times 5 would be 15, and if you subtracted 10, you would get 5. So I want you to try that with the next two. Be careful with number 2, because there's no place to plug that in. And if you're familiar with what we talked about in chapter 1, when it's just a number, we call that a constant function. So think about what that means. Look at your notes, and we'll talk about that a little bit tomorrow. The linear regression equation, basically they've given you some type of table representing some type of data, and they're wanting us to test like how close is the equation to the actual model given. So for example, if I was to plug in 2, negative 2 plus 19.7 is actually 17.7. And so I'm going to put that right here, 17.7, and you can kind of see those are fairly close. So that makes me think, hey, this seems to be a fairly decent model so far. So just continue to plug in different values from the table. Plug in 4, plug in 6, plug in all those values until you can see all of that table completed, and you can compare each predicted value. Last one I want you to work on is showing me you still can solve. We actually have variables on both sides with distribution involved. So I went ahead and kind of got the problem going a little bit. 4 times 3x, 4 times negative 6. Same thing on the right, 3 times 3x and 3 times 2. So try to see if you can get all the way to the end to tell me what the value of x is that solves the equation. Good luck, and I'll see you tomorrow.